Hello, my name is Paweł Parys and I work at the University of Warsaw. I'm going to present a paper called Higher Order Model Checking, Step by Step. So what is this paper about? There are three parts in the title which describe the content of the paper. First, we have higher order because we consider higher order recursion schemes. This is a formalism to describe trees which correspond to higher order recursion. Then we have model checking, because we solve the model checking problem, meaning that these higher order recursion schemes describe a model, which is a tree, and beside of that we have some formula or maybe automaton, basically some property. Which we want to check whether this model satisfies this property. And in our setting, this property is given by an automaton, more precisely by alternating parity automaton over infinite trees. And finally, we have the part step by step. This part says that we give a new method solving the model checking problem, and this method works in several simple steps. So this is step by step. Okay, let me describe this more precisely now. So what are these higher order recursion schemes? This is a generalization of context-free grammars, and in this generalization we have arguments. So every non-terminal can take argument, or multiple arguments even, and moreover, these arguments can be again functions, so they can take further arguments. So equivalently, this is just lambda calculus, but simply typed lambda calculus with recursion, with the recursion operator. Okay, and we use this kind of grammars to generate trees, but usually this will be infinite trees. Okay, we can also say that these are programs with recursion where we have further functions, so functions taking other functions as parameters, but like usually in lambda calculus, we have no data values, just functions, and moreover here in this setting every function has a fixed type, so everything, parameters as well. Yeah. Okay, now an example of such a recursion scheme. There is some alphabet of letters that will be placed in three nodes. So this alphabet is ranked, meaning that every letter has a specified number of children. So letter A, nodes with letter A will have always two children, and so on. We have three letters here, and we have these non-terminals that will be used in the grammar. Okay, and here are the rules of our example. These are some rules, and now how this works. So this S is a starting non-terminal we generate using the rule for S, and then we have a non-terminal A and some argument B. As you can see here, non-terminal A takes one argument F, and now this argument B is substituted for this F in the rule for big A. Yeah, we put B here and here, and we have we apply this rule, and now on the front we have a small a, which is a letter. So which means that we just generate a node with letter A. We put the first argument as a first child, the second argument as the second child, and we continue generating this. This BC here is just B with a child C, so we can draw it like this. And now we generate from this term ADB, we generate the left subtree. So we use again the rule for non-terminal A, substituting db for f. Okay, we have again something that starts with A, and now this right branch is a little bit more complicated because we have again a non-terminal D. We use the rule for D, which generates BBC, which we put here as a tree, and we continue like this. And the next branch will look like that. There will be 4b. On the next branch there will be 8b, and so on. So you see that the number of B-labeled nodes is 2 to power k on the kth branch. So this is a tree which is non-regular. So this kind of trees can be generated by such programs, by such grammars. One important thing is that everything has some fixed type here, so we can use this A only with an argument f, which is a function, so which takes a tree and returns a tree. So here this is the node like that. The letter O means is a type of a tree. And then O arrow O is a function that takes a tree and produces a tree. So for example, F is such a function, but also B, the terminal B, letter B, because it takes as argument a subtree and generates again a tree. Okay, and we have more complicated types like here. And this is a function that as a first argument takes a tree, and as a second argument it takes a function from trees to trees, and at the end it produces a tree. Okay, and one more important definition is order of a type. This order will be useful later. So what is an order? It means how complicated is the type. So it's 1 plus the maximal order of arguments. So for example, a tree has order 0, function from trees to trees is just of order 1, or maybe it takes more arguments, but all of them are trees. The order is 1. But if we take as an argument a function from trees to trees, which is of order 1, then the order grows to 2. Order of a recursion scheme is just the maximal order of its non-terminals. Okay, now we come to the problem that we want to solve. So first, the general goal is that we want to verify properties of trees generated by these recursion schemes. And why we want to solve it at all? So this recursion scheme, they model some programs using higher order recursion. So these are simplified programs for which the problems become decidable. So these are models of these programs, or abstractions of these programs. We want to answer some questions about programs. We cannot do this directly because this becomes undecidable, but we can approximate the program using a recursion scheme. This is typical situation in verification, yes, in model checking. Okay, and now more concretely, this is the problem that we solve. We have some automaton, more precisely this will be alternating automaton, and the acceptance condition is the parity condition. And moreover, we have this recursion scheme that generates a tree, and we ask whether this automaton accepts the generated tree. And this problem is known to be decidable already from 2006. It was shown by Luc Ong, and from this moment we already have multiple proofs using different techniques like written here on this slide. There are also some extensions which show something a little more. And there are also some proofs that work only for reachability automata instead of parity automata. And in this paper, I show some new proof, new algorithm, which has the advantage that it's a bit simpler, or at least it's different. Yeah, it's another technique. Okay. So, what do we know about complexity? The problem is n-fold exponential time complete, where this n is the order of recursion schemes. Yeah, so it depends on the complexity. The complexity depends on the order. Yeah, so it's the complexity is very high. So it looks bad, but actually in practice it's not so bad for two reasons. So first, the algorithms are fixed parameter tractable. They are linear in the size of the grammar. Yeah. So if this grammar is big, it's not a problem. The only part that goes to this exponent of this high complexity is the size of the automaton, and usually the automaton is smaller than the model that we want to verify. And moreover, the maximal arity of types in this grammar. Yeah, so arity means number of arguments. Okay, so we have this fixed parameter tractability. And moreover, it turns out that some of the algorithms behave quite well in practice, meaning they work relatively fast. It's not about our new algorithm. Here, in this algorithm, the complexity will be always, every case will be the worst case, but for some algorithms, mostly those based on intersection types, we have only some worst case examples where the complexity is really high, but quite often on several or multiple examples, the algorithm works fast. Okay, now let me explain a bit how this new method works. So as a first step, as like a pre-processing step, we consider a product of this grammar and of the automaton. This product will be again a recursion scheme which generates a tree of all runs of the automaton on the original tree. So this tree will be labeled by two things. Yeah, the name of the player, which decides in a given node, like in a party game, and the priority. Yeah, so actually the infinite tree that is generated is a parity game, and we ask who wins this game. Yeah, and this is like in the definition of acceptance of an alternating automaton. Yeah. So there are two players, and if player even wins, then the automaton accepts. Yeah. So we just expand the definition of acceptance by defining this product recursion scheme. So from now on, we just have a scheme. We don't have this automaton, and this scheme generates an infinite party game. And we ask who is this game? And this is the problem that we want to solve now. Okay, and now coming to the actual algorithm, how it works. It works, as I already said, it works in multiple steps, exactly in n steps, where n is the order of the recursion scheme. A single step is a transformation that replaces a recursion scheme of order n by a recursion scheme of order n minus 1. And this new recursion scheme will be equivalent in the sense that maybe it generates a different tree, or a different party game, but the winner is preserved. Yes, so the player even wins the game generated by the original recursion scheme, even only if it wins the game generated by the new recursion scheme. And we apply this transformation multiple times, exactly n times, obtaining at the end a recursion scheme of order 0, for which the problem becomes easy. It's just a finite party game that we have to solve. So this is something standard. Okay, and now let me explain this transformation, this single step where we reduce the order by 1. In order to understand this transformation, we should look at an application of the form KL, where this whole thing is of order 0, so it generates a tree, and where this L is of order 0, so it also generates a tree. Then the whole application, it generates a tree like depicted here, where this tree generated by L is put in some places below the context that is generated by K. So by context we mean some fragment of a tree which still has some arguments. These are the places where the argument is used, and there we just substitute L. And now, how a winning strategy for player even looks in such a tree. So what is a winning strategy? A winning strategy is a choice of some branches. There are some places where player even decides. Like here, he can decide to go to the right and see priority 4 and continue here. But in some other nodes, player odd decides and he might go left or right. So both these fragments are in the winning strategy. So this blue skeleton, it depicts the winning strategy that we consider. And now these numbers, they actually, these are priorities, maximal priorities seen on the whole branch from the root to the place where L is substituted. So for such a winning strategy, we can declare some number P, so that the greatest priority seen in the K part is either P or something better, where better, what does it mean better? It's described by the very natural order that is written here. So even priorities are of course better than worse priorities, yes, for player even. And small odd priorities are better than large odd priorities, and for even priorities the larger is better. Yes, so this is the often considered preference order. Okay, so this is about the number P. And now what happens in L? So if you know something about party games, they are positionally determined. So what you do next, it doesn't depend on what happened before. And this implies that when you already reach the subtree generated by L, it doesn't matter which copy of this subtree you have. You can just continue in every copy in the same way. So we may assume that this strategy of player even is the same in every copy of this L, except this copy where the strategy does not enter at all. Okay, and now what happens after the transformation? How we change it? So after the transformation, we reorder the things. Here, first player even declares this number p, this priority from the previous slide. So there is this choice on the top. Yes, and after this choice, so it's depicted only for p equals 3, but the same appears everywhere. So after this choice, it's a move of player odd, and he can either decide to check this declaration of p, or he can accept it. So if he accepts this p, so we just skip the k part, and we read this priority p, which is 3 in this case, and we continue in L. Yeah, the game continues in L, and here even has to win. Otherwise, we go to k, and now it's somehow and now player odd checks whether this declaration of p was correct. So to this end, we play in k, and here we cannot reach L, which means that for the places where the argument L should be placed, we substitute either top or bottom, which is a special tree where even either immediately wins or immediately loses. So on the branches where the maximal priority is indeed p or something better, this is okay, and there even wins. But on the branches where the maximal priority would be worse than this declared number p, even immediately loses. So intuitively you can see here some equivalence to the previous game. Yes, if there was a winning strategy, it can be transformed like here, and everything is fine. And you can do this also in the other direction. Yeah, you can compose this strategy. You can transform this strategy from here to the previous setting, where we have this L just substituted below this K. There are, of course, some details behind this general idea, but actually nothing really difficult happens in the transformation. To realize this, we have to duplicate non-terminals, so we have to make a copy for every value of p, so that if this k is a non-terminal, then we have a copy for every possible value of p. This k fragment, it can be also an argument of the whole rule that in which this kl appears. So we have to also duplicate arguments. We have to make a copy of every argument, one copy for every value of p. And as you see, maybe this transformation removes all arguments of order 0, so they disappear, and as a consequence, the order of every type and also of the whole recursion scheme decreases by 1. And for more details, you can see into the paper. There is a formal definition. Okay, to conclude, let me repeat what was done. We considered the problem of model checking recursion schemes against parity automata, and I have given a new method solving this model checking problem. I think it's a simpler method. In this method, we have a transformation which reduces the order of the recursion scheme by 1, and by repeating this transformation, we reduce the order to 0. At every moment, the size grows exponentially. We do n steps, so the complexity is n-fold exponential. If we look more concretely, there is still this fixed parameter tractability. Okay, so we have obtained the optimal complexity, the same complexity as of previous algorithms. That's all. Thank you.